Hello, my name is Charles Taylor, and I'm reporting for the refrigeration cycle experiment we did last week. So the objective of the experiment was to learn how to perform a full thermodynamic analysis of a heat pump, measure the coefficient of performance, the COP, and to draw and describe the vapor pressure curve on the pH diagram, the pressure and enthalpy diagram. So the vapor compression refrigeration cycle starts in 4 processes: the compression stage, the condension, the expansion, and the evaporation, and then cycles over again. These are driven by the 4 main parts: the compressor, the condenser, which is just a heat exchanger, the throttle valve, and the evaporator, which is just another heat exchanger. We see on the bottom, we have the ideal cycle for the pressure versus enthalpy diagram. We start at the vapor curve on the right-hand side, close to the vapor, go into the superheated steam region to 2, fall back through to 3, which is on the liquid side of the vapor curve, and then perform a constant enthalpic process down to 4 to repeat it over again. This is the curve we generated from our experiment, and the differences we see is that our curve does not end on the vapor side exactly. It goes into the superheated region and then goes back up into the superheated region again. So it doesn't just take right off from the most efficient point, which is on the curve. And also it decreases all the way down and actually decreases slightly past the vapor curve, going into the liquid stage, the full liquid stage. This poses a problem later in calculations because the tables actually don't list values for the full liquid stages. And then, but it did drop back into under the curve again and then come to complete the cycle. So still was a really good cycle, though we did have a lot of issues because of it. So the coefficient of performance, the theory behind it is that for cooling, you want the heat removed from the system over the work put into the system to cause that heat removal. The heat removal I used was that the QC, which is the rate of heat removal, would be the temperature difference driven by the water after the evaporator that the cycle caused. And then the second one would be the temperature difference driven by the condenser that caused the heat produced. The reason I had to go with this is because, like I said, on the curve, we went past into the liquid region and they don't state charts for those regions. I couldn't find any resources I had access to. So unlike using the enthalpy to calculate the coefficient of performance, I had to use heat rates, which is still valid in the process. This is a different method of doing it. So this is the predictive results from the leader last week. So we see 230, 275, about 100, and then the valve outlet is the same for the enthalpy. And so the coefficient of performance he calculated using the enthalpy method was 4.16. Doing the calculations, we get close in the results, 250, 270-ish, but H3 was unknown, like I said, because it fell in the liquid stage. So the property charts weren't available. One method we could use to calculate those is if we had the valve outlet and go backwards, but we would need to know the quality of the mixture, and that wasn't stated within the actual lab procedure, and the equipment didn't give that either, so that wasn't an option. So I had to go for this method I did do, using heat rates. So listed are the temperature differences between the condenser and the evaporator. And then we have the heat removed, the heat produced, the work done, which is collected by the motor. It's the electrical input put into the motor to do the work. And then you have the COPs we generate for the 3 different cycles we did for 3 liters per minute, 4.5, and 6 liters per minute. You see it's hanging around 2 up to almost 2.5, which is significantly less than the 4.16 we saw. It's a half less, it's 50% less. And so, like I said, we weren't running the most efficient cycle. We were going into the superheat region when we didn't need to and falling way into the liquid region when we didn't need to either. By trimming those down, you can produce a more efficient cycle. The uncertainties we see in this situation are mostly because it was self-done. There wasn't a lot of human interference, is that most of the uncertainties would be from the instruments itself. So most of the temperature sensors and the work sensors for the motor. And this is top of the generic equation. And then we have the total for the uncertainty for the total value of the COP we calculated, which is driven by the work sensor, and the QA, the heat removed, which the heat remove uncertainty itself, which gets put back in, is driven by the temperature sensors for both the 2 temperatures that we see on the evaporator side. Cool. Thank you. So the last part of this was to explain what a thermostatic expansion valve, or TXV, does and how it operates. So the device is used in normal refrigeration cycles to control the flow of the gases. So this leads to a more effective system because it's self-metering, you don't need to interfere with it, and it's more efficient that way because you don't have to put too much in, or you don't have to run as in non-optimal pressures. It will regulate to the optimal pressure for the system. So the way it works is the sensor bulb in the top region is filled with the same liquid, or a secondary part of the liquid removed from the system that expands at the same rate due to heat. So you have your input, which is on the hot side after the expansion, and it's going to the evaporator on the cold side, which is the B2. And how it works is that on the cold side, it generates a lower temperature, the bulb increases, it opens the pin valve, and allows more flow. Any questions?